Okay, so we're going to have a second session on vertical motion under gravity. Effectively, it's going to be a little bit more of the same, but with some slightly trickier questions. We're going to finish off that one example we still need to do from the textbook. And I'll also just further clarify a couple of key concepts which will be useful for answering certain types of questions. So to start off with, we've got the question on the slide here. It's that example of throwing something up in the air and seeing what happens. So if I throw something in the air at a speed of 10 meters per second, work out the maximum height. That should be sort of bog standard. You should know how to do that now using the Suvat equations. But quickly work it out, find out what that maximum height is. Remember, it's when the velocity is 0. And then the thing that I then want you to do is to draw what you think the displacement time graph for this looks like. So to be specific, I want you to draw the displacement time graph from the time when it first leaves my hand to when it lands back on the ground. Okay, so it's the full up and down motion. What does that look like on a displacement time graph? And there'll be certain details I'm looking for when you try and draw that. So give it a go, work out the maximum height, then draw the displacement time graph with key values on it. You can pause the video now, give it a try. Okay, so let's work this out. To work out the maximum height, we know that that's when the velocity is 0 instantaneously. S is the maximum height that I'm looking for, the maximum displacement. The acceleration, I'm going to take up as positive, in which case g is minus 9.8. It's fine if you took acceleration as 9.8, in which case down is positive. What else do we know? U was 10. Okay, and V doesn't matter. Oh no, it does matter, sorry. T doesn't matter. In this case, we're going to get V squared equals U squared plus 2AS. So that's 0 equals 100 minus 19.6 S, which gives me an S of 5.1, roughly speaking, meters. Okay. Now actually, to draw the displacement time graph, I said a moment ago T doesn't matter, but we should actually work out what the T is as well. So we know the maximum height achieved. Let's also work out how much time it took to get that high. So we're basically still going to take this information here, but now rather than S, I'm now asking what is T. Right, so we take note of the 5.1 meters. So I've got V equals U plus AT. So let's do a separate Suvat equation here using V, U, A, and T. That tells me 0 equals 10 minus 9.8 T. Therefore, T is equal to, and if I work it out, 9.8 over 10. Could have done that in my head, really. That'll be 100 over 98. Yeah, so 1 over that. So then we've got a value of about 1.02. Okay, so let's just make a note of what I've said here. Max height is 5.1 meters. Time to reach the max height in this case is equal to 1.02 seconds. So then the velocity, sorry, the displacement time graph is going to look something like this. We want the key features. So we've got time, we've got displacement. So let's mark on a few things. We know that at time 0, its displacement is 0, so it goes through the origin. At time 1.02 seconds, let's mark that there, it's at a height of 5.1. Let's mark that on. Okay. And then here's a question for you. So it takes about a second, 1.02 seconds to reach max height. How long do you think it takes to come back down to my hand again, or back down to Earth? You can prove this using Suvat equations. We'll skip it for now, but if you're interested, you can definitely prove this, and it's not too difficult using Suvat equations. It takes the same amount of time. So it's a symmetric kind of motion. In fact, the way it moves upwards, if you ignore air resistance, then it comes down in exactly the same way. So it will actually take a further 1.02 seconds. So at 2.04, it will be back at the Earth again, or back in my hand, right, or wherever we're taking as zero displacement. So that's three of the key points. And then the only thing here now I want you to think about is, how do we fill in the gap? So you might be tempted, for example, to do something like this to join them up. Or maybe you're thinking, oh, it should look more, like this, like a curvy sort of motion. Or maybe you're thinking, it's more like something like this. It depends what you're thinking. In terms of how does displacement change with time, right? Remember, this is technically not a picture of the throwing, because the throw happens in one dimension. It goes up and it goes down. It's not going across. It's not a projectile, right? It only goes up and down. But two of these must be wrong, at least. Is the displacement changing constantly with time? Is it changing faster, or is it changing slower? So to answer this, what we can do is we can think about the formula for displacement, right? So that is, using Suvat, S equals ut plus a half at squared. So if you think about it, t is kind of like our x-axis variable, right? So it's kind of like our x. I'll put it in quotes. It's the x-axis, and the s is our output. It's kind of like the y, so it's the value on the y-axis, displacement, and the other numbers are just constants, right? Because u in this specific case was what? It was 10, and a half a in this case, so that's half of 9.8, isn't it? 4.9, but minus, because we're taking up as positive, so minus 4.9. So what we actually get is the following. Let's write it in purple. S equals 10t minus 4.9 t squared, right? And if you notice, double check the key values. Do they work? So when I put in 0 for time, I get a displacement of 0. And then I just tried it on the calculator. If you put 1.02 into here, you'll get 5.1. And if you put in 2.04, you'll get back to 0 again. Technically something like 0.000, because we've rounded when we said t is 2.04. Okay, so this is actually the graph. Think of it as y equals 10x minus 4.9x squared. What does that graph look like? It's an upside down U shape, isn't it? Because if you're plotting a quadratic, if you've got something that's minus a constant times x squared, it's going to be an upside down U. It's going to be the N shape. And then you just have to think about, where does it cross the y-axis? In this case, at 0. And if you completed the square for this, you would actually get your maximum value, which in this case is 5.1. So it's the blue, right? It's the blue one is correct. So if you drew this, then that would be perfect, right? With these three values, actually, you should also indicate this is 0, 0, just to be clear. And with that kind of curve shape, that is the displacement time graph. The justification for why it's curvy, well, you can justify it many ways, but the easiest way to clearly see it is to find the equation. Okay, so I'm just going to talk about this a little bit then. this concept of writing an equation for the displacement time graph and also the velocity time graph. Okay, so I'm just going to talk a bit about this concept more generally of writing s as a function of time, right? So this is making a displacement time graph or a displacement time function for an object. So I'm just going to write out the 5 equations, and we're just going to analyze why I can or why I can't use each of them to form this kind of function. Okay, so the first one is actually perfect for this, right? I would use this if I want to plot the displacement time function, right? So that is to say, I want to plot displacement against time, and I want a mathematical expression that tells me what that is. And what you need to do is you need to know what the initial speed was, u. You need to find the acceleration. Perhaps it was given to you, or maybe you need to work it out. And then you'll write the function in that form. Right, s equals ut plus a half at squared. Sometimes that expression will be quadratic. If the acceleration is 0, so it's constant speed, then it'll be linear, right? Because this half at squared disappears, and you just have s equals ut. But that's your sort of catch-all. S equals ut plus half at squared. That will work as a displacement time function. If we look at this one, now you might be tempted to rearrange this. Oh no, sorry, for this one it's more obvious, sorry, why we can't use it. T is not in there. It's as simple as that. Okay, so this one we can't use to write a displacement time function because there's no t. Okay, so this one is then the one for which you might be tempted to use it. So you might be tempted to use this to write the displacement time function. However, I think it's better to avoid it for the following reason. The amount of time that something moves for is what changes its final velocity, right? If I say, an object's accelerating at 1 meter per second squared, if it's been doing it for 5 seconds, its final velocity will be 5, assuming it started from rest. If it's been doing it for 10 seconds, now its final velocity is 10. So in some ways, this v is kind of a function of t already, right? If I change t, I'm changing the final velocity. If I change how long it's been accelerating for, I'm changing the final velocity. However, you contrast that to this one. Your initial velocity just is your initial velocity. It doesn't matter how long you've been going for. If I say, oh, my initial velocity was 2 meters a second, and now I've been accelerating for 5 meters per second squared for 17 seconds, all of that is unnecessary information. You've already told me the initial velocity. Whereas if I don't know those things, I can't get the final velocity. So the final velocity is more like a function, and the initial velocity is more like a constant. So it's a very subtle thing, but I would avoid using this because v is itself a function of t. If you don't fully understand that explanation, I would say don't worry too much, but please just take away from this that this is the function you want to be using. Okay. So then this one here, v equals u plus at, there's no s, so we can't obviously use it, but as a bonus, this is good for plotting velocity time graphs. Okay, so if you wanted to plot the velocity time graph of a scenario, or you were asked to, then this is how you would do it. Yeah, you'd get, again, initial velocity and acceleration, and you would write v equals u plus at. And that's your function. V on the y-axis, t is the x-axis. And then finally, this one I would again avoid using, and it's for similar reasons to the previous one. Here, it's that v is itself a function of t, and therefore v is not really a constant. It changes depending on what your t value is itself. Okay, so let me just rub out the bad and leave the good. And ultimately, this is what we need to conclude. If you're going to draw a velocity time graph or displacement time graph, use these two appropriately. And as we'll see in a moment, even if you're not interested in drawing the graph, if you just want to understand the motion of a particle, particularly the displacement, create this function for the object, and you'll be able to see, like, oh, at this time it's at this position, and at this time it's at this position. It's quite useful. It's an alternative to just sticking in a specific t value. It's to write a function of its motion, and then you can more broadly see what's going on. You can see if it's quadratic, you can see if it's linear, and the example will make clear why we want to do this. Okay, and next, this is nothing too difficult, I don't think, but I do have to warn you, this is a slight deviation from the textbook, because I think the way it's taught in the textbook is a bit confusing, and there's a far simpler way of understanding what I'm about to tell you. Hopefully that doesn't sound too vague. So what I'm telling you, you won't find in the textbook, but I think it makes things simpler. And I'm trying to think of how to call this. I'm kind of calling it the more accurate Suvat equation for displacement. So all I'm going to say is there were 5 Suvat equations, and one of them so far has been a little bit, not a lie, but a bit inaccurate, or at least not general enough, right? The other 4 are completely fine as they are. So the one that I want to tweak is this one. Okay, and just to be clear, it's not wrong at all, but it has an underlying assumption. Okay, and the assumption is this. This works if you assume initial displacement is 0. Okay, and in a lot of scenarios that is what you want to assume, right? Because in many scenarios, by definition, you'll say, you know, what is the displacement from the starting point? Your starting point is therefore defined as 0. Okay, but if you think back to the previous video, there was one scenario where something started at, I think it was 7 meters, so it didn't actually start at 0. And then to compensate for that, we said, I'll pretend it is 0, do the calculation, and then add 7 back at the end. Now that is one way of doing it, but I think there's a better way, which is to use the more general version of this formula, the version that works for all cases. Okay, and that version of the formula, it's not too difficult. It's this. It's the same thing, but adding in one more additional constant. Okay, and all this is the initial displacement. Okay, so if you look at the new version, which is the one that I think we should start sort of thinking about generally, it's basically the same, and in fact when S0 is 0, it is the same, right? Which makes sense, because the whole point is this works when your initial displacement is set as 0, right? When you say the starting point is my 0 displacement point. But if it's not, then you'll use this version. Okay, so by default S0 is 0, but if you're told in the question, or you're given a scenario where you are already displaced, then I will use this version of the formula. And then you don't have to worry about trying to, you know, create a new 0 point and then adding it in at the end. You can just use the formula directly. And also, just in case you're worried that I'm you know, sort of teaching you, you know, just my version of things because I prefer it, this is actually completely legitimate. If you look up equations of motion on Wikipedia, if you look in sort of higher level textbooks, this is what they'll use. They'll use this S0. It's very standard notation, but for whatever reason it just doesn't seem to be taught in this particular textbook that we use. I think it makes things a lot simpler, and it makes sense because if you think about it, we already use u, right? We talk about velocity as being v, and then we say the initial velocity is u. So u is like the special case of v. And then we say, well, the displacement is s, but for some reason we've not included an initial displacement. And you could have used another letter, but I guess they just used s0, right? Naught meaning at time 0, that's why there's a naught there. It's saying the s when the time is 0. In some ways, u is basically v0, but instead of using v0, we just write u. So it's slightly, the convention is sort of not consistent, but don't worry about that, as long as you can understand that u is the initial version of v, s0 is the initial version of s. But because the initial velocity tends to not be 0, we give it its own letter, and the initial displacement, very often it is 0, so it's just not bothered giving its own letter. But technically, that's where it would go. Okay, so now that we've got that, I think we're just about ready to tackle the example. One last thing I want to mention before we do. Okay, mathematically, what does it mean for two objects to collide? Here's my question. So, I mean, I guess the question is there. It is what it is. If two things hit each other, what does that actually mean? What's the definition of two things hitting each other? So have a think about that. So just to be clear what I'm asking, I suppose, if I say, what's the definition of achieving the maximum height? In terms of Suvat equations, you could say it's when the velocity is 0, right? That I suppose that's not technically the definition, but a result of the definition. In this case, with the collision, we want to be a bit more precise, or we'll be more close to the actual definition. So what does it mean? Two objects collide. So the answer is, mathematically speaking, it means they have the same displacement for the same, how should I phrase this better? I won't say for, they have the same displacement at the same time. Okay, or in layman's terms, what I'm effectively saying is that they are in the same place at the same time. Which seems a bit obvious, but I mean, effectively, in terms of the universe, everything at a specific time is in a certain place, and things can occupy the same place but at different times. That doesn't count as a collision. So a collision of objects is only when it's both the same place and the same time. If they go there, one after the other, doesn't matter. That's not a collision. So it's same place, same time. So what that means in terms of Suvat equations is, if you have your s value, displacement, for one object and the s value for another object, and you can show that they're equal at some t value, some time value, then there's been a collision. Okay, cool. All right, so I think we're ready to tackle the example. I think that's been enough build up. Okay, so here we go. A ball A falls from rest from the top of a tower 63 meters high. So let's do the tower. This is going to be ball A. From rest, and the tower is 63 meters high. At the same time as A begins to fall, another ball B is projected vertically upwards from the bottom of the tower. So let's have our B over here. And this one's going up. So this one's going up at 21 meters per second. and this blue one initially, it was from rest, so it's initially 0 meters per second. So this picture I'm drawing is the initial conditions. And as you can imagine, because of gravity, A will start falling down, and B is initially going up, though gravity will eventually slow it down. But at some point they hit each other. Find the distance of the point where the balls collide from the bottom of the tower. In other words, let's just draw a line. Let's say they collide here. The question is asking, what is that distance? Okay, so how high up is the collision from ground level? Okay, so here's what we need to do. We're going to create functions of time for each of these two objects. In order to do that, we need to find a few things. We need to find the u, and we need to find the a, so the initial velocity and acceleration for each of these objects, which isn't too difficult. I just want to be careful though of notation. So for a, its u is 0, and for b, its u is u is 21, or is it 21? It depends. It depends on if I'm taking up as positive or down as positive. Now, it doesn't actually matter. Let's take up as positive. Either way, we'll still get the right answer. If we take up as positive, okay, then it is 21. The only problem is now I've got two things called u on the page with different values. It doesn't really make sense. So here's how I suggest you properly write out the working for this question. If you want to be good in your sort of mathematics, make it readable, then this makes a lot of sense. You want to subscript your variables with the object to which it pertains. So that u there is the initial speed of a, so I'm going to call it u subscript a, and this u I'm going to call u subscript b, just to make it clear which one's which. Okay, and then for the object a, what's its acceleration? So that's the little a acceleration of the object a. If up is positive, then that means acceleration is going to be negative because the object's going down. It's going to be negative 9.8 due to gravity, right? And likewise with b, it's also the same. It's going to be negative 9.8. I'm just going to rewrite that u here because it looks a bit too much like an a. Okay, that's marginally better. So we've got u, we've got a in each case. What about the initial displacement, right? So again, I couldn't talk about this unless I'd briefly introduce it, so I'm hoping you understood that. The initial displacement of b, S0, we're going to have to do multiple subscripts here, S0 of b is 0, because I'm choosing to take the ground as the 0 point. Okay, so the ground, the earth on which the tower sits, that's 0. And that's what I've decided. And then for A, we've got an S0 of 63, right? Because its initial displacement is not on the ground, its an initial displacement is up here. Okay? Right, so now let's write the equations for each of these objects. So the S displacement of A is going to be equal to ut plus a half at squared. So that's u of a times t plus a half the a of a t squared. But I forgot to include the S0. So let's just erase that and include the S0 because it's not 0 in this case. So the S of A is equal to the S0 of A plus UAT plus a half AT squared. It looks a bit ugly because of all the subscripting, but it does make it clearer what we're referring to. It becomes nice now when we put the numbers in. S0 of A is 63. U of A is 0, so the UAT goes away. And then minus 9.8 halved is minus 4.9, and I get this. Okay. So this is telling me the displacement of A at any given time. Test it out that it makes sense. Do a sanity check. When t is 0, what value do I get? 63. That makes sense because at time 0, A is at 63. As t increases as time goes on, what happens to S? It will decrease because we've got a minus sign here. So the 63 will be getting smaller and smaller and smaller, which makes sense because as the object falls closer to the Earth, it's getting closer to the Earth. The S is becoming smaller, the displacement. Okay, and now let's find the SB. So that's going to be S0 of B, which is 0, plus UB times T, which is 21, T, minus a half acceleration of B T squared, which again is minus 4.9 T squared. Okay, so a little bit different looking equations, partly because one of them had initial speed of 0 and the other one had initial displacement of 0. So here you've only got a t squared, whereas here you've got a t and a t squared. Okay, so here's what we're saying. If you pick a value of t, you'll be able to get the position of these objects at any given moment. So when I do t is 0, I get 63 here, and when I do t is 0 for b, I just get 0, which makes sense. So I want to find a t value at which both of these are the same, right? So effectively, I'm just going to be solving a quadratic in a moment. SA equals SB for which t value, right? In other words, at what time are their displacements the same, which means they hit each other. So I'm going to just clear up a bit of working now, make some space, and just focus on the two equations that actually matter. So it's these two in purple. We're effectively just going to solve these. So we're going to equate them to each other, get a quadratic, and see what ends up happening. So we've got 63 minus 4.9 t squared equals 21t minus 4.9 t squared. And as you can see, the t squared, the minus 4.9 t squared, are going to cancel from both sides. Super easy. So you get 63 equals 21t. Conveniently, 21 goes into 63 perfectly. It's t equals 3. Okay, so what that tells us is after 3 seconds exactly, they will hit each other. So now, to finally answer the question, what's the distance of the point where the balls collide from the bottom of the tower? We now need to find the corresponding s. So all we do is put t equals 3 into either one of these equations and we'll have the answer. And it doesn't matter which one we put it into because the answer should be the same. Because at the point they collide, they'll be in the same place. So for instance, if I do 63, I'll do it on the calculator, minus 4.9 times 3 squared, I got 18.9. Right, that was at t equals 3. And for the other case, if I do 21 times 3 minus 4.9 times 3 squared, oh, it's quite obvious actually. Again, you just end up with 18.9. So that's the answer. They collide at a height above the ground of 18.9 meters. Okay. So the things that were new in this example that we hadn't used before were making use of this S0. In this case, it was 63 for the object A. It was 0 for object B. And then the second thing is this concept of leaving S as a function of t rather than just plugging in a t value and getting a number. Because when you've got them as a function, you can do far more interesting things. You can compare them to other objects, see when they collide, or see how far away they are from each other at a given time, all that sort of stuff. Cool, all right. I think then you can try some questions of our own. And there'll be at least one which is similar to this for you to practice. Okay, so I've got 3 questions total. Just these two here And then there's one challenge one on the next slide, which is it's quite short looking. It's worth giving it a go though. See if you can do the challenge question. That would be quite nice. The first question that you can see here is pretty much what the example was that we just did. So while it's fresh in your mind, see if you can answer it. Obviously the numbers are different. Give that a go. 13 is a nice one. It's using suvat a couple of times to see subsequent bounces of an object bouncing up and down. And then finally you've got the challenge on the next slide. So give these two a go. When you're ready, you can pause the video. Okay, and here is your challenge. I quite like this one because it feels a bit similar to two things hitting each other, but instead it's this interesting idea. I throw a stone, 2 seconds later I throw another one. If they hit the ground at the same time, how high is the building? It's a good one. So you'll want to find S as a function of t for both of them, and then think about what things you need to equate if they're hitting the ground at the same time. You can pause the video now.